Hello everyone, welcome to online classes on building structure 6. In today's session we are going to continue about a retaining wall or a retaining structures. In last session we have studied about retaining walls, which are nothing but retaining structures or retaining structural elements which retain the material from disturbing the main structure. And there are different types of retaining wall, like gravity retaining wall, cantilever retaining wall, counterfort retaining wall, and buttress retaining wall. We have also studied about forces or pressures acting on a retaining wall, like earth pressure, which will be a lateral earth pressure, especially in dry soil condition, in submerged soil condition, in partially submerged soil condition, as well as surcharge weight, effect of surcharge weight. So in today's session, let us study about failure of a retaining wall or a failure modes of a retaining wall, and as well as detailing of a retaining wall. So there are 4 different modes of failure. Let us study one by one. First one is by failure of a retaining wall by a overturning movement, or you can say simply a overturning. Whenever there is a earth pressure or a soil pressure which is acting from, say I have a retaining wall, this is a stem of a retaining wall, a vertical one. This is a toe slab of a retaining wall, and this is a heel slab of a retaining wall. Say this was the dotted line are the original positions of a retaining wall. Now I will apply a soil pressure or a earth pressure or a backfill pressure. So whenever I apply a backfill pressure, this retaining wall, which is originally in this position, must resist this earth pressure predominantly. If it doesn't have that much of a capacity to resist this soil, then what happens is, if the slab is not stable enough, then this may happen that the movement which is caused by the horizontal earth pressure, which we can call it as a overturning movement, if this movement is in more than the resisting movement, that is in the opposite direction, then overturning of a wall will happen. That is, this wall will turn into this position, and a wall fails. So remember, overturning by failure mode occurs only when overturning movement exceeds the resisting movement of a structure or a retaining wall. Second case is by sliding in a sense. Suppose I have a retaining wall in this position and I have a backfill. When I apply a force or a pressure, even though the stem is much more stable and the overturning movement is also in range, but it may happen that the slabs which are connected to the soil are not strong enough, and there might be less friction in the frictional force is not enough to resist the horizontal pressure applied from left to right side. So because of this entire retaining wall may slide along the horizontal axis, and this is called as a failure mode by sliding, and this happens only when earth pressure is more than the resisting force. Third case is pressure distribution below the base because of the pressure distribution, or you can simply say it as a soil pressure from the base. So you can see here a soil pressure from the base. I am applying, this is a retaining wall, this is a backfill side, and this is a free side. So I'll draw a pressure distribution like this. Then I'll be having one point or the center of this triangular element where this pressure will be concentrated. Consider the backfill weight as W2, which is acting on the heel slab. This is a heel slab and this is a toe slab and this is a stem. So the weight of a soil which is acting in this portion, I'll consider it as a W2, and this W2 will have a certain center of gravity, and the total weight of that soil will be acting along that center of a gravity. Now, and this is a center of a gravity of a retaining wall, or you can say a stem. So here, whenever these two, that is W2 and PA, active earth pressure, and the backfill soil which is on the heel slab, will act together at a resultant, along the resultant line, and this resultant line will be acting at any point on the slab of a retaining wall. From all these forces, I'll be creating a pressure, earth pressure or a soil pressure, which will be maximum at the toe end and minimum at the heel end, and certain value will be there. Now, if the resultant force is acting in within the 1/3 of this total length of the total width of the retaining wall, then it will be a safer side. If that is 1/3 of in the length, in the sense, suppose this is a total width B, then I'll divide this B into 3 parts. Then the resultant must act within the middle part of the width B. And if I substitute this as a in terms of Cartesian coordinates, it should be B/6 on left side and B/6 on the right side, and that is what we call it as a minimum eccentricity. E should be within B/6, or E should be less than B/6. Then this P max at a toe should not exceed SBC of a soil. This value, maximum pressure at the toe slab, should be lesser than safe bearing capacity of the soil. Otherwise, this retaining wall will fail. And P minimum, that is P2 at heel, should be a compressive type. Otherwise, heel will be lifted above, and the soil which is not permissible, and heel will be lifted above the soil, and if the heel is lifted, then the retaining wall will fail by overturning. Last, fourth type of a failure mode is due to bending. So we all studied that whenever there is a force or a pressure acting from this side, this stem will bend as a cantilever type, as well as heel will also bend, as well as a toe will also bend. This portion is kind of a fixed type of a fixed nature, and these three components act as a cantilever element or a cantilever action. So this deflection of a stem, deflection of a heel slab, deflection of a toe slab will cause a certain stresses at these junctions, and this is where a bending failure may occur. If this stress exceeds the critical stress condition, then because of that a bending failure may occur. So this is the reason why we provide a reinforcement on this side. That is, when I apply a pressure on this side, this will be a cantilever action, So on this side it is a tension side and on this side it is a compression side. So I am providing a reinforcement in this way. And on the heel slab, when a backfill load is acting in a downward direction, there will be a soil pressure from the below, as well as because of this there will be a sag in the heel and a sag in the toe and a hog in the heel, and this will cause a tension on the upper side and a compression on the lower side. So reinforcement will be on the upper side in the heel slab and on the lower side in the toe slab. Let us study about few of the proportioning guidelines as per Indian standards for retaining walls. First one is width of a retaining wall. A minimum of 200 mm is a top width of a retaining wall stem. Then bottom width of the stem, it is designed depending upon the maximum bending due to horizontal earth pressure. Width of a base slab, that is a total width of a retaining slab. This depends upon whether the retaining wall is with surcharge or without surcharge. If it is with surcharge, then I can take up to 0.5 times of a total height to 0.6 times of a total height. And if it is a retaining wall with surcharge, then I can take it as a 0.7 times of a total height, where h is the overall height of the wall. Then toe projection in the sense width of the length of the toe wall, or width of the toe slab, and that I can take it as h by 6 or b by 3. Minimum depth of foundation is given by p by w, 1 minus sin phi divided by 1 plus sin phi to the whole square, where p represents SBC of a soil, w represents density of earth, and phi represents angle of repose of a soil material. This is a typical example, or this is one of the example of a reinforcement arrangement in a retaining wall. This is a cross section of a retaining wall. You can see here this projection. This is called as a shear key. This rectangular or a box type of a provision is called as a shear key. This shear key will help us in avoiding or in retaining the sliding failure of a retaining wall, and as well as it carries certain forces. Let us start with the reinforcement one by one. So I'll start with the stem portion of a retaining wall. This is a heel slab, which is a bigger one. This is a toe slab. Wherever the heel slab is there, on that side backfill will be there. So I am applying a backfill in this region. So if backfill is in this region, the soil will be acting a pressure. Soil will there will be a earth pressure from right to left side on this stem, and because of that this stem will bend as a cantilever in this manner. So when it bends in this manner, this side of the stem will be under tension, whereas this side of the stem will be under compression. So since it is a tension on this side, I will provide a main bars on this side. So you can see the main bars are 12 mm dia at 90 mm center to center. Now earth pressure will be maximum at a centroid of a stem height, and that is at a distance of h by 3. So what we do is we provide main bars as well as a distribution bars. Distribution bars, you can see there are distribution bars. Okay, 8 mm dia at 150 mm are the distribution bars. Okay, now main bars I am providing 12 mm dia at 90 mm center to center. These main bars are important to carry the main tensile force of the which is acting on the stem. Since the maximum earth pressure will be at a distance of 1/3 of a stem, what I will do is till 1/3 height I will provide the full amount of a reinforcement, that is at 12 mm at 90 degree. After that I will reduce it to a certain extent. I can reduce it to certain extent. So from h by 3 to h by 5, suppose this is a total height which is 4000 meter, so 4000 mm, 4000 divided by 3, whatever value I will get, for till that length I will provide 12 mm dia. You can see here 12 mm dia, which are vertical bars at equal intervals of 90 mm center to center. Once I complete that h by 3 value, I can curtail alternative bars, and this curtailment I will do it till h by 5. So here you can see I am curtailing this bar at this distance, and I will provide alternative bars till h by 5. So here these bars are at a distance of 12 mm dia at 180 mm center to center. Again, once I go upper side on the next level, I can curtail another distribution bar. So I am providing 8 mm dia at 12 mm dia at 360 mm center to center. So this is about the stem reinforcement on the backfill side. On the other side of a stem reinforcement, I have to provide a minimum quantity of a reinforcement, and that I have calculated it as a 8 mm dia at 300 mm center to center throughout the length. And again these are again subdivided into main bars and distribution bars. Main bars are the vertical ones and distribution bars are the dotted ones. Then on the heel slab, so heel slab will hog in this manner. So on the top face it is a tension side, and on the bottom face it is a compression side. Since the depth of the slab is just 200 mm, or thickness of a slab is just 200 mm, no need to provide a reinforcement in two layers. So I'm not providing any reinforcement at the bottom, whereas I'll provide a full amount of a reinforcement on the top. Here also I'll be having a main bars and distribution bars. I am providing 12 mm dia at 180 mm center to center as a main bar, and 8 mm dia at 180 mm center to center as a distribution bar. And these main bars will run into the heel slab, then the stem section, and then it will get projected to a certain development length into the toe slab for a better interlocking. And the stem slab, which is coming from this end, will continue as a reinforcement in the toe slab because it gives a better interlocking system. So in toe slab, the slab will deflect in terms of sagging, and because of that we need a reinforcement at the bottom, and at the top it's not necessary to provide a reinforcement. So since I need a reinforcement at the bottom, what I'll do is I'll bend this stem slab or stem reinforcement and bend it into the bottom side, and this reinforcement I am providing as 12 mm dia at 180 mm center to center as a main bars, and 8 mm dia at 180 mm center to center as a distribution bars. So this is a typical cross-sectional arrangement. Here you can see there is a slope which is provided for toe and heel slab. You can provide a straight slab also, or you can provide a slope also. Both options are possible. And this is a typical arrangement of a reinforcement on the length side for a stem reinforcement. Similarly, there will be a arrangement on the toe or a slab side, slab in terms of a slab. Thank you very much for the session.